Hello, I am Václav Novotný and welcome to the tutorials of energy sources and conversions. In this tutorial, we will have a look at the real fluid properties and their diagrams, specifically at the enthalpy-entropy diagram, and we will have a look at the steam Rankine cycle. So, now we will start to address the cycles with the phase change. The fluid property during their phase change has behavior much different from the ideal gas, and therefore we will start using real fluid properties. These can be provided, for example, in form of diagrams, tabulated values, or more complex functions and correlations, typically as computer programs and add-ins into them. In this course, we will use mainly diagrams due to their illustrative value. Once the principles are clear in the diagrams, it is easy to use the same principles, but in an automated way in your computers and programs. So let's have a look at some of the diagrams. The fluid that will be shown in them will be water, respectively steam, which we can see here on the right side. Previously, we were using the air, which we can see on the left side, and you can see that the air also has phase change, but at very low temperature. The area of the diagrams, here of the TS diagrams that we were using and we will be using, are shown in the red boxes, where we can see here on the left hand side that we were using only superheated state of the fluid, where the behavior is already quite close to the ideal gas, while here for the water, the area that we will be using contains the phase change and contains highly non-ideal properties. So what can we see in the diagrams? In the all diagrams that are shown here, we can see the curve of the saturated liquid in blue and saturated vapor in the red. Between them is the mixture of gas and liquid, for example, droplets in the gas or some small bubbles within the liquid. Here in this TS diagram, we can see in the gray lines of constant quality. That means constant ratio of the mass of the vapor state compared to the liquid state. Further on, we can see here in the solid lines the isobars, lines of the constant pressure. These are important for us because many of the processes we will be using and considering are isobars or very close to them. Then, illustratively, you can see here lines of constant enthalpy, the dashed blue lines, which further in the right in the superheated fluid become nearly horizontal, because there the behavior is close to the ideal gas, where the enthalpy is function only of the temperature. And compression, pumping or expansion for ideal change is the isentrope. Those would be vertical lines in this diagram. Despite its illustrative value, the TS diagram is not suitable to perform practical calculations. Here comes handy the enthalpy-entropy diagram, which is shown here on the right side. Again, we can see the line of the saturated liquid, saturated vapor, we can see the isobars, and we can see the lines of constant quality. Of course, any state property can be used in the diagrams. As an example can serve, for example, the pressure enthalpy diagram shown in here, which is specifically suitable for and very often utilized for cooling cycles, where it's advantageous due to the clearly show the isenthalpic throttling, which happens typically in the throttling valve in the cooling cycle or refrigeration cycle. Then we can see the lines of constant entropy, which can be used for the compression. Then we can see quite specific shapes of the lines of constant temperature, isotherms, which of course at single pressure they are constant in the two-phase, but then as we go further into the superheated state, their shape is going almost vertical, meaning isenthalpic change, where the enthalpy becomes only a function of the temperature, as for the ideal gas. And of course, we can use, as I said, we can use any two-state properties. So just for illustration, here on the right hand side, we can see the temperature volume diagram. Now let's move to the Rankine cycle, the elementary cycle with phase change. We can see the process flow diagram here on the left hand side, where we have liquid, in ideal case in the saturated form, as the saturated liquid here at the state 1, which is then pumped to the state 2 into the subcooled liquid. Then there starts isobaric heating process in the boiler, going from the point 2 to the saturated liquid state, saturated vapor, and then superheating before we expand the steam in the turbine between 3 and 4. The end of the expansion might be in superheated vapor, but much more often, especially for water and steam, the end of the expansion is in the wet steam state. That means there are some of the liquid droplets in our gaseous fluid. And then the last part, so that the cycle would work, is the heat rejection. We have to reject the heat in the condenser between the point 4 and point 1. So you can see the area in this TS diagram, the area 1, 4, 5, 6 is respective to the heat rejection, while the area 6, 2, 3, 5 is respective to the heat addition. If we subtract these two, heat addition and heat rejection, we will get from the basic energy balance the net work output. And here on the right hand side, we can see the same cycle illustratively shown in the enthalpy entropy diagram. Again, having some work of the pump 1 to 2 and work of the turbine 3 to 4. Since work of the pumps or turbines is just difference in enthalpy, so here once we get the enthalpy values, we can clearly get the work. And also during the isobaric processes, the heat exchanged is again the change in the enthalpies. So change in enthalpy 3 and 2, for example, would be the heat addition. Change in enthalpy 4 to 1 would be the heat rejection. So we will calculate a first problem of the Rankine cycle. So consider the Rankine cycle with steam parameters at the outlet of the boiler at 2 megapascals and 450 degrees C. Then the condenser pressure to be 7 kilopascals, and the net power output of the system would be 100 megawatts. We want to get the pump work and turbine work, efficiency of the cycle, and we will show two methods, one precise and one approximate. Then get all the parameters in the nodes of the cycle and determine what is the required amount of cooling water flowing through the condenser. The assumptions are following. We will assume the isentropic efficiency of the turbine and pump to be 100%, ideal pumping and ideal expansion. There will be no pressure drops in the system. At the condenser outlet there will be saturated liquid, that means no subcooling. And the cooling water in the condenser will be heated up by 10 kelvins. And for determination of the parameters and properties, we will use the enthalpy entropy diagram If you want the enthalpy entropy diagram, you can use, for example, the link in the description of the video. So let's draw a table of with the nodes in the system of the cycle and put in the parameters that we already know and see how we obtain further ones. So we were provided with the parameters at the turbine inlet at the point 3, which were the pressure 2 megapascals, 2000 kilopascals, and the temperature 450 degrees C. So those are two inputs that we had. And the other input was that the pressure in the condenser at the turbine outlet at the point 4 is 7 kilopascals. So before we get to using the enthalpy entropy diagram, we can directly get some of the other parameters. Because we assumed no pressure losses in the system, so we can see that the pressure at the point 3 will be the same as the pressure at the point 2, or the intermediate pressures in the saturated liquid state, 2', or 2" at the saturated vapor state. So the same 7 kilopascals as is in, so the same 2000 kilopascals, 2 bars, is also in here. Here and here. Similarly, for the condenser there is also no pressure drop, so points number 4 and 1 will be both at 7 kilopascals. So we have the pressures in all nodes of the system. Now, in the state number 3, we have pressure and temperature. Those are two independent thermodynamic variables, so we'll use them and the enthalpy entropy diagram to get the enthalpy and entropy. So here you can see a big enthalpy entropy diagram for steam. You can see in description that where was chosen the reference state, which is at 0 degrees C and respective saturation pressure, and that in this point the entropy is chosen as 0 kilojoules per kilogram Kelvin and enthalpy also as 0 kilojoules per kilogram. Also you can see for example, the bottom limit of the diagram, which is triple point of the water and respective pressure and temperature. And now let's see the curves in the diagram. The curves going diagonally to the right and top side in the wet steam area, and then following on are isobars, where for the isobars we have the given description pressures up here and then eventually here on the side. Then the lines which are in superheated state, where the fluid behaves similarly as ideal gas, where they are horizontal, and then they turn down towards the saturated curve. Those are isotherms. Then the isotherms and isobars in the two-phase area are the same. And of course, on the y-axis we have the enthalpy, on the x-axis we have the entropy. So let's try to find our state at the turbine inlet. So the temperature at that point was 450 degrees C. So we can see the isotherm 450 over here. It's this one. And the pressure at the turbine inlet were 2 megapascals. So we can see P equals 2 megapascals is this line in here. So we can follow this line, isobar of 2 megapascal, and we can find the point at the turbine inlet. So once we find the intersection of the isobar and isotherm, we can read the value of the enthalpy on the y-axis, which is, in our case, this is 3300, 3350, and something more. The exact values from the calculation programs say 3358. Now let's get also the entropy for this point. The entropy, you can see it should be somewhere here, 7, 7.1, 2, 3, 4, 5, so 7.35 approximately. So that's the point at the turbine inlet. Now how will the expansion look like and what will be the state at the turbine outlet? Since the turbine is ideal, that means the change is reverse adiabatic, which means isentropic. So in this diagram it will be vertical line going down. So let's make a vertical line and go down to the pressure 7 kilopascals. So we have that line in here, and now where are the 7 kilopascals? Here we have 1 kilopascal, here we have 4 kilopascal, here we have 10 kilopascal. So 10, 8, 9, 7. It should be this line over here. And the isobar then continues into the two-phase. And the cross section is over here. Again, let's get our ruler and see from this point the turbine outlet enthalpy should be 2270 approximately. The exact value says 2263. Also, since we are at this point, so let's see what will be the condensing temperature. At this point of the saturated vapor is the point of departure of the isobars further up, and isotherms going into the nearly horizontal state in the superheated area. And we can see that we have isotherm 50 degrees C over here. So this is 50. So here at 7 kilopascals it should be approximately 40 degrees C. So the temperature would be approximately 40 degrees C. And lastly, since we are here at the turbine outlet, we can see also what is the steam quality. The steam quality are these curves. So, and they have their legend over here. So you can see 70%, 75, 80 and so on. So from this point, if we follow the respective curve, we can see that the steam quality is approximately 88%. So x equals 0.88. So now we can go back to our table and fill in respective values. So the enthalpy at the turbine inlet was, if we get the exact values, so 3358 kilojoules per kilogram. And we obtained it as a function of pressure and temperature. These functions and temperatures, this consideration of it as a function of pressure and temperature is especially important if you would consider some computer programs for, or not only computer, now you can get also mobile phone applications with the steam properties and so on. So you, in these systems, you say that you want the enthalpy as the function of this pressure and this temperature. Now just short information regarding the fluid properties applications. So you can really find steam tables for your mobile phones or as computer programs and add-ins into, for example, Microsoft Excel. There are free libraries such as CoolProp, or you can get some more advanced but not free libraries as RefProp. If you want just water and steam, there are add-ins such as one called XSteam. So just CoolProp, RefProp, XSteam. So you can use especially CoolProp or XSteam as they are free easily also on your own computers. So this was the enthalpy. The entropy, we estimated something as 7.35. If we get the exact values, or if we work more precisely with the diagram, we should get that the value should be 7.287. And again, it is a function of pressure and temperature. The steam quality at this point doesn't make any sense because it's in a superheated area. And then we had the isentropic expansion. So the entropy after the expansion is the same as entropy at point 3, which is this 7.287. And the enthalpy that we obtain for that is from the diagram 2263 kilojoules per kilogram. How we would obtain it by using computer programs. Now it would be function of the pressure, which we have in here, and of the entropy, because we assume the isentropic expansion. And the temperature that we got, we estimated as approximately 40 degrees C. If we get more precise values, so we get that it's the value is 39. And we can again get it as function of pressure and entropy, but in general we got it as the saturation temperature at given pressure. So the saturation temperature at given pressure means that we search for the temperature as function of the pressure and quality, which equals 0 or 1, or basically anything in between. And lastly, the quality, we estimated 88%. The precise value is 87.2, 0.872. And again, we used it for the point with given pressure and entropy, so we can use it like this. Or since we already know the other parameters such as the temperature or enthalpy, it could be, for example, pressure and enthalpy. Pressure and entropy or pressure and enthalpy are always independent variables no matter of the fluid state, but definitely we cannot use at this state in the wet steam function of pressure and temperature, because there is the same pressure for the same temperature for the whole range of the steam qualities. Now let's have a look at the remaining nodes of the cycle. In the point 1, over here, we said that the condenser outlet is at the saturated liquid point. That means the quality at this point 1 is 0. So that's one of the inputs into the system. Then about the point 2, we don't know anything yet. But point 2 prime, here we can see that it's also on the saturated liquid curve, so there would be also quality 0. And point 2 double prime is a point at the saturated vapor curve, so the quality would be 1. So, if we were using the correlations of thermodynamic properties, we would already have two independent thermodynamic variables, the quality and the pressure. So, we could write that all temperature, enthalpy and entropy would be function of pressure and quality. But now let's use our enthalpy-entropy diagram and other information to obtain these values if we don't have these correlations and if we don't have these functions. So let's start with the point 2 double prime, the saturated vapor at 2 megapascals. So let's go back to our diagram, and we already have here the isobar to megapascals, and we just continue on this isobar further down up to the point of the saturated vapor line. And at this point, intersection with the saturated vapor line, we can get the enthalpy from this point, which is apparently just under 2800, and we can also get the temperature. We can see that the isotherm going from this point is this one, which will be apparently 210 degrees C. So 210 degrees C and 2800 kilojoules per kilogram. Now if we want to continue on the isobar down, so we can see that we cannot get in this and basically any enthalpy entropy diagram, you cannot get reasonably to the line of saturated liquid. But what you can do is to advantageously use the fact that the enthalpy is linear function with the steam quality. So we can read, for example, steam quality at 80% over here. So let's take, for example, steam quality of 80% and get the enthalpy for this point. And we can see that the enthalpy would be approximately 2425 kilojoules per kilogram. And before we go back into the table and calculations, Let's do the same thing for the low pressure side of the cycle, for the 7 kilopascals. So again, let's see what will be the enthalpy at some specified steam quality. So for example here at the 70%. So let's move the ruler. Here, and cross section of this isobar and the line of the constant quality at 70% would be over here, which is at enthalpy of apparently pretty much exactly 1850 kilojoules per kilogram. And now the last value that we will get from the enthalpy entropy diagram will be the enthalpy of the saturated vapor at the low pressure. So we have the isobar at 7 kilopascals, and we find its intersection with the saturated vapor line, which is over here. And for this point, we will read the value of the enthalpy at the y-axis. So from this point over here, this is 2500, 2550. So the value will be approximately 2570 kilojoules per kilogram and Kelvin. So let's fill these values into our table, where first the point 2 double prime, the enthalpy was estimated as 2800 kilojoules per kilogram. If we get the exact value, so it would be 2798.3. So you can see we were fairly close. And the temperature was estimated as 210 degrees C. The exact value is 212.4. So again, you can see pretty close. Yeah, we did not get the entropy at that point, but we don't need the entropy at these two auxiliary points for any reason. Now let's see the point 2 prime, where since it's the single component fluid, so the boiling temperature is constant at the constant pressure. And the enthalpy, we did not have the diagram wide enough, and there anyway it would be two lines which with very small angle between them, with hard possibility to find the intersection. So we will show how to do that in a short while. But we made two auxiliary points. Let's name it A1 and A2, where the first point to help us was at 2 megapascals, and at the specified enthalpy, at the specified quality at 80%. And the second point was at the low pressure at 7 kilopascals and at the specified quality of 70%. And the enthalpies we estimated were for the high pressure side and 80% quality it was 2425, and for the 70% at the low pressure it was 1850. And the last auxiliary value that we will use is the point number 7. You can see it over here in the TS diagram, for example, the point at the low pressure and at the saturated vapor. So the point number 7 is at 7 kilopascals. The steam quality is 1, it's the saturated vapor. And from our diagram we obtained the value of enthalpy of approximately 2570 kilojoules per kilogram. Now let's get the values of the saturated liquid from the saturated vapor and point at the specified quality. So as I said before, the enthalpy in the two-phase is a linear function of the steam quality. So for the heat of evaporation, often denoted as HFG, we can write that it is a ratio of enthalpy of saturated vapor minus enthalpy at some specified quality divided by the difference in quality between the saturated vapor and this specified point, which in this case would be 1, steam quality at the saturated vapor, minus this specified quality. To get the enthalpy at saturated liquid, it's nothing but the difference of enthalpy at saturated vapor minus the heat of evaporation. So we can write that the enthalpy at the saturated liquid is enthalpy of saturated vapor minus the ratio minus this heat of evaporation which we derived up there. So it looks like this. Now for our given values, let's say for the point number 2 or points number 2, so H2 prime as saturated liquid would be the H2 saturated vapor, which we know, minus the friction H2 saturated vapor minus H at the specified quality, which was for the point, it's here this point A1, so 80%, so x equals 0.8 divided by 1 minus 0.8. So H2 double prime is 2798.3 minus again 2798.3 minus this point 2425 divided by 1 minus 0.8, and the result from this will be 931.8 kilojoules per kilogram. So this point would be 931.8. So this is the value that we obtained from the approximate values from the diagram. The exact value should be, however, 908.5, and just see where is the difference. The difference is in the determination of the enthalpy in this point, because the exact enthalpy for steam quality 0.8 and 2 megapascals would be 2420.33, and the moment we use this value in our calculation, so it would be 2420.3, suddenly we get the value of 908.5, which is the exact value also obtained directly for the pressure and quality. So 908.5. Now let's do the same thing for the point number 1, the saturated liquid at the low pressure. So we use basically the same relationship, just over here we will have H1 and this is, now we cannot use the H4, we need to use the point at the saturated vapor line, so it's the enthalpy at point 7, H7, minus, and again H7 minus Hx, where x now was 70%, divided by 1 minus 0.7. Now why didn't we use again 80% as here? It's because larger span we get, more accuracy we get. So if our diagram allows us to go not just to 80% but to 70, let's use 70 and you get more precise result. And now let's put in the values that we had. So enthalpy at point 7 was 2570. 2570 minus 2570 minus enthalpy, auxiliary enthalpy A2, 1850, divided by 1 minus 0.7, and the result which we would get would be 166 kilojoules per kilogram. So over here would be 166. Now again, this assumes that we have this is a result of the approximate values of the enthalpies that we had both at the point 7 and at the point A2. If we get the precise values, which would be not 1850, but it would be 1849.2, and over here would be 2571.7. So we would get exact value at the point 1, which should be 163.3 kilojoules per kilogram. Yeah, now we're also missing the temperature here, but the temperature needs to be same as at point 4 because it's single component working fluid with just condenses, no pressure losses, so the temperature stays the same. And now the only point we are missing is the point number 2. And again, if we would be using some computer correlations or if we would be using some functions for the steam and water properties, so the change of the properties in the pump is isentropic in the ideal case, which is in here. So that means the entropy would stay the same. So entropy at the point 2 will be the same as entropy at point 1. And then enthalpy would be function of the pressure and entropy. If we don't have these functions, we will use the first law of thermodynamics and the fact that we have a liquid, which in ideal case is incompressible, but still we will need to use one more parameter, and that will be density. And for the density, you can use some steam tables or things like that, from which we would get the value of the density as 992.6 kilogram per cubic meter. In order to get the point 2, let's have a look at the first law of thermodynamics. We can write, or you might know, that the du is dq minus pdv. Change of internal energy is the change of the transferred heat minus pressure times change in the volume, the change in volumetric work. Now, the definition of enthalpy goes that the H as enthalpy is internal energy plus PV. And if we differentiate this term, so we will get the H equals du plus pdv plus vdp. Now let's combine together the first equation and the third one. So we can write that the H is dq minus pdv, and now plus pdv plus vdp. We can see that the pdv's cancel out. And we can see that the change in enthalpy, the H, is dq plus vdp. Which we can also write that change in enthalpy is change in the transferred heat plus change in technical work. Now, how do we apply it in getting the point number 2? So, it's isentropic process. Isentrope is reverse adiabat, so transfer of heat with the surroundings is 0. So for adiabatic process, we can write that the H is change in technical work, which is vdp, and the unit volume is inverse of the density, so we can also write that it's dp over density. Now, since the process in the pump is using liquid, which is nearly incompressible fluid, so the density is a constant, and then we can write that the change in the enthalpy is change in the pressure divided by the density. And enthalpy at the point 2 after the pump will be enthalpy at point 1 plus the change in enthalpy, which is enthalpy at point 1 plus change in the pressure divided by the density. In our case, the enthalpy at the point 1 is 163.3 kilojoules per kilogram, and then we sum it up with the pressure difference. Since this is in kilojoules per kilogram, so we can also use the kilopascals directly here as the units. So change in the pressure would be 2000 minus 7 divided by the density, which was 992.6 kilograms per cubic meter. And getting the exact values, so it's 163.35 plus 2.01, which is 165.36 kilojoules per kilogram. So we can insert the value into our table. So it's 165.36 kilojoules per kilogram. And yeah, what is missing here? Again, the steam quality does not make any sense. It's since the fluid is in subcooled state. And the last thing, which is temperature. Normally the temperature could be determined also as function of pressure and entropy. Since we also want to make some estimate, so what we can do, it is not very accurate, but because it's valid just for ideal gas, but we could say that the change in the enthalpy in ideal gas is Cp times change in the temperature so in that case change in the temperature would be change of enthalpy divided by specific heat capacity, which is 2 kilojoules per kilogram divided by approximately 4.2 kilojoules per kilogram in Kelvin, which is roughly 0.5 Kelvin, or more precisely 0.47 Kelvin. However, if we get the exact value, so we will see that the temperature would just rise very slightly to 39.06. So we can see that the temperature rise is merely negligible and actually much smaller than what we would expect from applying the ideal gas relation. So now we have the values of all the parameters in the table, well, except for the entropy, but we don't need that one at this point. And we can continue in the calculation of our problem, where the task was at first to determine what is the heat input and what is the work of the turbine. So for that, let's again use the first law of the thermodynamics, actually already the part which we have had over here. change in enthalpy is change in the heat transfer plus change in the technical work. First, for the isobaric heating process, since it's isobar, so there is no change in the pressure, so dP member would be 0. There is no technical work done by the working fluid. So the relation shrinks into dH equals dQ, or we can write it in differences that change in the enthalpy equals change in the transferred heat. So the heat input into the system we can write as change in the enthalpy free at the end of the heating process minus enthalpy 2 after pump at the beginning of the heating process. Getting the values there, so it's 3358 minus 165.4, and the result is 3192.9 kilojoules per kilogram. Similarly, we can get the rejected heat. Q out. Which is difference in enthalpies after the turbine, which is enthalpy 4, minus enthalpy at the end of the condenser, enthalpy 1. So the enthalpy at the turbine inlet is 2263.5 minus at the outlet it's 163.4, and the resulting difference is 2100, pretty much exactly 2100.1 kilojoules per kilogram. Now for the work of the turbine, let's have a look again at the definition of the enthalpy, where dH is dQ plus technical work. The technical work is the work of the turbine we want to get, and when we have adiabatic process, so this equation will not have any, or there will be no heat transfer with the surroundings. So the equation shrinks to just dH equals change of the technical work, and then work of the turbine is again difference in enthalpies, delta H, and it will be enthalpy at the turbine inlet, which is enthalpy 3, minus enthalpy at the turbine outlet, enthalpy 4, which is 3358 minus 2263.5. As a result, we will get 1094.7 kilojoules per kilogram. And work of the pump, well, again it's a difference in enthalpies, which we already calculated before. And where did we have it? We had it over here, that the work of the incompressible liquid would be change in the pressure divided by density, which was 2.01 kilojoules per kilogram. Now, with these relations, we can get the net work output of the system, and we have basically two methods how we approach the energy balance. Now let's have a look at the energy balance and the notation that we will be using. So we will have a look at what is the work and heat input, work and heat output. All of these values will be used as absolute values, and then of course for the steady state operation, the sum of all work and heat input minus sum of work and heat output needs to be 0. So we can write. Now we can also use just unit parameters, since there is just one stream with one mass flow rate, which is not changing anywhere throughout the cycle. Sum of the work input plus sum of the heat input minus sum of the work output minus sum of the heat output equals 0. So what is the work input in our case? It's the work of the turbine. The heat input is the Q in over here. Work output is the work of the pump, and heat output is rejected heat over here. This can also serve as a check if our calculation is correct. So let's just try to put there the values by yourself. And depends how precise were your values. In my case the result was plus 0.05, and probably the main reason of inaccuracy was in the determination of the pump work just from the assumption of ideal liquid. Then some minor discrepancies might be also as a result of the inaccuracy in the thermodynamic properties, but especially for water and steam, there the correlations are really very accurate. So now, when we have established the energy balance, we can also see what is the efficiency of the system. The efficiency of the system or the efficiency of our cycle is the ratio of the network output divided by heat input. The heat input is directly determined in here. The network output is the difference between the work of the turbine, which produces work, and work of the pump, which consumes work. From the energy balance, we could also see that the network output could be determined as difference of the heat input minus heat output, because the overall energy balance must always work the energy cannot just disappear or originate out of nothing. So we can also write that the network output is the Q in minus Q out, and still divided by the heat input, which is the Q in. So now let's see the values. The work of the turbine was 1094.7 kilojoules per kilogram minus work of the pump 2.01, and heat input was 3192.9, and the result is 34.22%. And for the second case, using just the heat values, so heat input 3192.9, and heat rejected was 2100.1, and again we should get 34.22%. Now, in the problem statement, we were talking something about approximate way to calculate the efficiency. You can see that the work input is very small, so in some very rough and quick calculations, you could perhaps neglect it. So, what would happen if you would neglect it? So, approximate value of the efficiency could be also just, and only in case of Rankine cycle, where the work of the component that pressurizes the working fluid is very small. So it could be the work of the turbine just divided by heat input, which is 1094.7 divided by 3192.9, and the result would be 34.29%. So you can see that for some really quick estimates, the values are not that different, but of course when we calculate precisely, we need to include all the heat and work in the system. Now, the problem statement said that we want to calculate the parameters also for the network output, absolute network output of 100 megawatts. And the question is, what is the mass flow rate of the steam within the cycle? And for that, basically we can say that the network output as absolute value is unit network output multiplied by mass flow rate of the working fluid, here of the steam. So from that we can get that the mass flow rate of the steam is the ratio of the absolute network output divided by unit network output. So in values, it's 100 megawatts, so 100,000 kilowatts, divided by the network output that we had over here, 1094.7 minus 2.01, 91.5 kilograms per second. And the last question was, what would be the mass flow rate of the cooling water? So for that, we will use again the energy balance of the heat exchanger. So the Q rejected in the condenser. So let's say Q out in steam needs to be the same as Q of the cooling water, the heat that the cooling water accepts. The heat rejected by the steam is Q out multiplied by mass flow rate of the steam and for the mass flow rate or for the heat of the cooling water, we can use the calorimetric equation where we have the mass flow rate of the cooling water multiplied by specific heat capacity of the water and multiplied by temperature difference of the cooling water. Now we know the rejected heat and the mass flow rate of steam from over here, or also we will calculate how much is needed per 1 kilogram of water in the cycle. The specific heat capacity of the water is for approximately 4.2 kilojoules per kilogram and Kelvin, and temperature difference was 10 kelvins in the problem statement, which is the typical temperature difference applied in systems like the condenser. So the mass flow rate of the cooling water is the heat in the steam divided by specific heat capacity times temperature difference, which is rejected heat was over here 2100.1 kilojoules per kilogram multiplied by mass flow rate of the steam in kilograms per second and specific heat capacity of water approximately 4.2 kilojoules per kilogram and Kelvin, and temperature difference was 10 kelvins. So the result, also we can check the units, kilojoules, kilojoules, 1 over kilogram, 1 over kilogram, 1 over Kelvin and Kelvin, and what remains here is just kilograms per second. And the resulting value is 4576 kilograms per second. Or if we would calculate it just per 1 kilogram of the working fluid, so here would be just 1. And we could see that for each kilogram per second of the working fluid circulating in the system, in the cycle, we will need 50 kilograms per second mass flow rate of the cooling water in the condenser. So you can see that the 4.5 cubic meters per second approximately is a really large amount of water that needs to circulate between the condenser and cooling towers. And when you sometime go to actual power plant, so please notice the dimension of the pipes going into the condenser and from it in the cooling circuit. At the end of this tutorial, we will have one more problem. Let's assume that we have a Rankine cycle with the same parameters as we just did, but now the turbine and pump will not be ideal devices, but we will assume that they have some isentropic efficiency. For the turbine, it will be 90% and for pump 80%. And our task here is to get the turbine and pump work, to have a look at how the heat input and output would change, and also to have a look at what will be the new cycle efficiency. So first, let's have a look at the real expansion. The inlet parameters of the turbine will remain the same. There is still the specified pressure and temperature at the boiler output. Then the turbine will work between the same pressure levels. The inlet stays the same, the outlet is given by the condenser. So we are still operating between two isobars with given starting point. And how the expansion will look like? We have it shown partly in here, where here on the TS diagram you can see that the starting point is the same and we always go into the same isobar. The real expansion is a process that, as basically any real processes in nature, produces entropy. So therefore the entropy rises during this expansion. So the expansion line is no more vertical, but it is inclined slightly to the right, as we can see here. And in an extreme case of very low efficiency, the expansion might actually end up even in superheated steam, still at the same isobar. We can see the same thing in the enthalpy-entropy diagram here on the right, where we had the ideal expansion, vertical line, then expansion with some given efficiency, which is inclined a little bit to the right, and then in case of very low efficiency of the expander, we can end up the expansion process in the superheated vapor. Now let's have a look how to include our efficiency into the calculations. So, any efficiency is always ratio of output against the input. So for our turbine efficiency, for our turbine isentropic efficiency, this ratio will be the ratio of the output, which is the net work of the turbine, or real work. Let's call it W turbine real. And the input into the process is given by ideal work of the turbine, which is basically the difference in ideal enthalpies. So from ideal difference in enthalpies, we get real work of the turbine. So let's call it, for example, delta H ideal. So what will it mean with respect to our problem? Or first, let's also rewrite it in general terms. So the real work of the turbine would be enthalpy of turbine inlet minus enthalpy of the turbine outlet for the real expansion, and the difference in the ideal difference of enthalpies is just enthalpy of turbine inlet minus enthalpy of turbine outlet ideal. With respect to our Rankine cycle, it will be the enthalpy of the turbine inlet is enthalpy H3 minus real turbine outlet will be H4 real, and here we will have still H3 minus and H4 because it was ideal expansion. So now we can find the expression for the outlet enthalpy. H4 real, and it will be the enthalpy at the inlet. Let's first write it. Enthalpy inlet minus ideal enthalpy difference multiplied by the efficiency. So it will be the enthalpy H3 minus now the enthalpy difference for the ideal case, which is H3 minus H4, and this will be multiplied by our turbine efficiency. Now let's have a look at the pump. So this was the turbine or expander. And now let's go for the pump. Now how will this ratio look like for the pump? The output of the pump is getting from one pressure level to another. So the output in this case will be the ideal difference in enthalpies. That's what we want to achieve. And the input of the pump is the work that is necessary to run it. So it will be the enthalpy of the pump outlet minus enthalpy at the, maybe we can also put here the ideal, minus enthalpy at the pump inlet, where the inlet again stays the same. And now the real difference will be just enthalpy of the pump outlet for the real pump minus still the same starting point at the pump inlet. So with our numbers of the cycle, it will be the enthalpy H2 minus enthalpy H1 divided by enthalpy H2 real minus H1. And now how to get this enthalpy H2 real after the real pump? Well, similarly as it was for the expander case, we will start again with the starting point. Here it's Yeah, let's put in H in. But now the enthalpy is increasing, so it will be H in plus ideal enthalpy difference divided by the pump isentropic efficiency. So we have the starting point, we have ideal difference in enthalpy, but the real difference in enthalpy will be larger. We will go further right in the diagrams because the entropy is increasing. So let's put in numbers, or let's put in notations of our. So let's put in notation of our Rankine cycle. So it will be H1 plus, and now the ideal enthalpy difference, which is H2 minus H1 divided by the pump isentropic efficiency. Okay, now we have the equations set up, and let's put in the values. So for the expansion, the enthalpy at the turbine inlet, H3, is 3358 kilojoules per kilogram, and minus again 3358 minus ideal enthalpy at the turbine outlet is 2263, and multiplied by the efficiency of the turbine, which was 90%, 0.9. Putting this together, we get that the enthalpy at the turbine outlet as 2372.5 kilojoules per kilogram. So you can see it's actually indeed a little bit higher than the original one. Now let's do the same with the pump. So enthalpy at the pump inlet, H1 is 163 kilojoules per kilogram, plus the ideal work of the pump, H2 minus H1, was 2 kilojoules per kilogram, and we divided by pump efficiency, which is 0.8. So we will get to the enthalpy H2 real as 165.87, again kilojoules per kilogram. Okay, now we can put these values also into our table. So at the point 2, the enthalpy at the turbine outlet was 165.87, so you can see still not much of a difference. And the enthalpy at the outlet of the turbine, this was outlet of the pump, and outlet of the turbine was 2372.5 kilojoules per kilogram. Okay, if you would like to get the temperature at this point, the best way to do it would be to use the two independent variables that we now have. It's still the pressure at the pump outlet, and we have the enthalpy. So similar as we had function of pressure and entropy, so now we will have function of pressure and enthalpy. And if we would actually run the numbers through some properties functions, so we would get the temperature that it would be 39.18 degrees Celsius. So again, not much of really difference of the temperature at the pump. Now for the outlet of the turbine, it's at 7 kilopascals. Again, we have the enthalpy, So for obtaining the temperature, it's best always to use the function of pressure and enthalpy. And same function could be also used, for example, for entropy or for the steam quality. Now let's check the temperature and steam quality also in the enthalpy-entropy diagram. How do we get the new point of the turbine outlet in the diagram? Well, we just mentioned we are still at the same isobar, and we calculated the enthalpy. And the enthalpy was 2372, so we can try to find 2300, 2350, about here should be, or here should be 2370. So let's take our ruler, and our point of the outlet, of the expansion outlet, will be intersection of the isobar of 7 kilopascals and here this enthalpy. So we can actually draw the expansion line. So the expansion line will look like this. So now we can also see that we are still in the wet steam area, and we can check what is the new value of the steam quality. And here we have steam quality of 90%, and this is approximately, this is 91, this should be approximately 92%. Also, since we are in the wet steam, so the temperature stays the same at 39 degrees C. So the temperature stays 39 degrees C, and we found in the diagram that the steam quality was approximately 92%. If we run the numbers exactly with properties functions, it would be 91.7. So we were pretty close. Alright, so now we have calculated again all the values for in the nodes of our system. And now let's go to the last part, looking at the change in the work and change in the heat input and output. So the real network of the system will be network of the turbine minus network of the pump. Well, network of the turbine is the difference enthalpy H3 minus H4 real, minus, and the work of the pump we had here, work of the pump would be H2 real minus H1. But also we can write it in this way, that it's work turbine ideal multiplied by turbine efficiency minus work of the pump divided by pump efficiency. So the real work of the turbine will decrease from 1095 kilojoules per kilogram to 1092.9 kilojoules per kilogram, and the work of the pump increased from 2.008 to 2.06 kilojoules per kilogram. So the work of the turbine decreased from 1095 kilojoules per kilogram to 985.5, and network of the pump increased from 2.06 to 2.575 kilojoules per kilogram. The resulting network of the cycle decreased from 1093 kilojoules per kilogram to just 982.9 kilojoules per kilogram. Now what does it do with the heat input and heat output? The heat input stayed nearly the same. There was very small change in the enthalpy at the pump outlet. So the Q in is still H3 minus H2. The H3 still stays as 2263. And enthalpy at the point 2 just increased very slightly to here 165.87. And the value of the heat input into the cycle is 3192.13 kilojoules per kilogram. The rejected heat, on the other hand, increased a little bit more because of the turbine outlet, which is in now considerably higher entropy, and it's H4 turbine outlet minus H1 condenser outlet. So H4 we calculated over here minus H1 stays the same, this 163.3 kilojoules per kilogram, and the resulting rejected heat from the cycle is 2209.15 kilojoules per kilogram. So we can compare these two values with the values we had in our previous calculation. So actually heat input in the ideal state was just slightly larger than in the real state. Is because of the pump outlet being a little bit at larger entropies, but still the difference is less than 1 kilojoule per kilogram, and the heat outlet, the rejected heat from the condenser, is more than 100 kilojoules per kilogram larger now. Now let's get the cycle efficiency. Get the cycle real, which is the ratio of the, for example, network, or always it's the ratio of network to heat inlet, 30.8%. So we can see that the effect of real turbine and pump efficiency, which still can be considered 90% of the turbine as rather optimistic, decreased our efficiency from 34%, more than 34, to almost 31%. So the decrease in efficiency is almost 10%, because it's about 3.4 percentage points from the original one. And 3.4 from 34 is 10% decrease in power plant efficiency. Okay, so that's all for the first tutorial in Rankine cycles.